Good afternoon. I am Gordon Tate, now Dounreay Site Innovation Manager, but prior to that I have had a 40-year career covering both reactor operations and reprocessing plant decommissioning. The site tends to be underestimated by many people, so I will start my presentation with a short history to put things into context. The Dounreay Nuclear Power Development Establishment, to give it its original title, was commenced in 1955 to explore the potential of the fast neutron reactor design, which incorporated the unique feature of being able to breed additional fuel at a time when the country was short of fuel supplies. The site is thus famous for the iconic Dounreay fast reactor pictured here, which was the first fast breeder reactor in the world to generate and export electricity to the national grid, and indeed it provides us with its own decommissioning challenges. However, the site contains more facilities and functions than most people realise, as it also contains a full suite of fuel reprocessing and manufacturing plant for both the plutonium fuel cycle and the uranium fuel cycle, as well as post-irradiation research facilities. That is because the site was home to both two fast reactors and a material test reactor. The site has seen spent fuel that was burnt on site being reprocessed and then fabricated into new fuel, which was then reprocessed in the site's reactors. This capability was not just confined to the site, but was also provided for materials test reactors around the world. So in this sense, it is probably the most diverse nuclear site in the world in terms of breadth of capability. Other sites may be physically larger, but had a more focused product stream. To further increase the reactor types, the site joins that of the Royal Navy Nuclear Shore Test Facility containing two pressurised water submarine test reactors. These discussions are underway to include them in the Dounreay decommissioning scope to further increase the range of reactors being decommissioned. I will now give an update on reactor decommissioning progress on the site, highlighting achievements, challenges and future plans. I will start with the materials test reactor, as it has been shut down the longest and decommissioning is the furthest advanced. The reactor was shut down in 1969 after 11 years operation and defueled by 1971. The reactor then sat until 1996 when further work took place to see Stage 2 decommissioning largely complete by 2001. This included removing all bulk heavy equipment from upper floor levels to reduce later lifting requirements, and also reduce the safety risk of suspended loads on the intermediate floors if the reactor was subject to a longer care and maintenance period than planned at that time. Inspection work inside the reactor vessel to assess the radiological conditions supported the plan to defer the next phase of decommissioning for 20 years, by which time the primary radiation source from the underside of the top shield plug shown here would have decayed to an optimum point, with further delay not bringing any material benefit of alternative decommissioning methodologies or techniques. In addition, the majority of reactor block materials that have a relatively short decay period have now essentially moved from intermediate level waste to low level waste category, although we will be storing some waste for a short time to complete this transition. The time delay from operations has therefore also reached an optimum point for reducing long-term waste disposal costs. The reactor is now having the remainder of the peripheral equipment stripped out to clear the containment building ready for the reactor block decommissioning. Here we see the top plate from the fuel element storage block being removed. The current plan for the reactor block is to first remove remaining components such as small shield plugs, residual components in the mortuary holes, and then the aluminium tank. These will be removed by lifting out and grouting into 6 meter cube boxes. The remaining bioshield will be low-level waste and will be cut up with diamond wire into blocks suitable for loading into the half-height ISO containers. Now, the Dounreay fast reactor decommissioning is making good progress. The ancillary generating plant was removed early in the programme to allow space to support the reactor dismantling. There were two key challenges to the decommissioning of the reactor vessel going forward. The first was presence of the liquid sodium-potassium coolant. As well as being highly chemically reactive, it was also highly contaminated due to the use of operation of vented metal fuel. There was also the additional problem of a stuck driver fuel rod, and approximately 1,000 remaining breeder elements. Distortion or material damage to a number of these elements in service meant that they were not removed following reactor shutdown in 1977. The first problem to be addressed was the liquid metal coolant. A dedicated process plant was constructed to deal with this, and so the liquid metal coolant has been successfully removed, neutralized to a salt, and discharged as waste following ion exchange to remove the bulk of the contaminants. This was completed in 2012. This has exposed the remaining reactor internals for viewing to allow a better understanding of the challenge of fuel removal. There are essentially two problems here: fuel element distortion and those where material damage has rendered the original handling mechanism inoperable. The distortion of breeder elements has been an acknowledged problem for a long time, having been identified back in 1965 when difficulty was first experienced removing them. The cause was identified at the time as inadequate cooling in the breeder area surrounding the core. It was not possible to carry out a redesign to fully rectify this problem, so to address the issue at the time and return the reactor to operation, sections of reactor top plate were machined out and removed to free certain elements. A number of elements were dealt with, sufficient to refuel the reactor, with the remainder being left for later. The initial decommissioning plan to remove the material was to use a multifunctional machine which could use a variety of tools to deal with all eventualities. In the event, this proved too challenging to deploy and highlighted the importance of accurate and faithful mock-up trial facilities. To test the machine, a mock-up representing 1/4 of the reactor top circumference had been constructed. Unfortunately, this did not identify the subsequent problem of cable management in operation, which was required during actual deployment as it did not replicate the full rotation required. To address this problem, a fresh approach was taken. The fuel removal task was broken down into discrete challenges with appropriate tooling developed for each one. This initially made use of the original reactor refueling design intent as its basic operating method. Approximately 50% of the remaining fuel was undamaged, and so the original collet latch arrangement could be used for its removal. This then created space to develop suitable tooling to retrieve damaged elements. Removal of elements also clears sections of top plate, allowing sections to be cut away, further improving retrieval access for the more problematic ones. The revised tooling has been working well, and despite a reduction in productivity due to COVID, we have now removed over 75% of the material. It has not all been plain sailing though. During early removal work, and just when things were getting into a steady rhythm, there was a problem with a fracture of the main crane rail. The fuel is removed by a shielded flask and traversed via the in-sphere Goliath crane to the discharge port. This suffered a longitudinal fracture, displacing a section of the rail outwards by about half the web thickness. The investigation into this fault identified that the circular crane rail, which runs at operating floor level, was not as circular as it should have been, and after nearly 60 years of service, rubbing by the main wheels on the edge of the rail had finally caused a crack and displacement of the railhead. This required a replacement, initially of the defective rail, but ultimately the full circumference. This was particularly challenging due to the infrastructure in the way restricting access, and also difficulty in procuring suitable rail, as the original railhead profile was obsolete, requiring a significant effort to obtain the correct profile, which included a search of various scrap metal dealers. Nevertheless, this challenging task is being overcome to allow fuel removal to continue. The work is being done in sections to minimize the impact on the fuel removal program and maximize the reprocessing program, with limited arc crane operations being carried out to support this. The breeder fuel elements are in the form of slugs of uranium encased in stainless steel tubes. And if you look on the picture on the left, you can see some nice examples of good quality uranium. The original process plant for dealing with the breeder was no longer available to support the process, so a dedicated process cell line was constructed adjacent to the sphere for this purpose. Once the rods were extracted from the reactor and loaded to the process cell, the plan was to extract the slugs by slicing the tubes along their length to open them up, and then either reprocess or store the material as appropriate. A decanning machine was designed and constructed for this, but inactive trials identified some issues, as it failed to cope well with distorted rods. This was redesigned based on experience gained from the decladding of 11 tons of material removed some years ago, where a small in-cell machine was developed to declad cropped lengths of breeder fuel rods. This took place around 2008 and had encountered the full range of quality varying from the pristine quality, as you see on the left, to the heavily oxidized slugs that you can see on the right, and provided valuable operating experience. And you can see here the variety of the material that we had to deal with. Now to move to PFR. The prototype fast reactor had a 20-year operating career, commencing generation in 1974, and with the final shutdown in March 1994. It was a good test bed for proving the potential of fast breeder reactors with a range of fuels and construction materials tested while working in a power generation regime. There were also a number of significant challenges which had to be overcome by innovative engineering, such as secondary heat exchanger tube plate design and the recovery from the oil ingress to the primary circuit from a failed primary sodium pump bearing seal. Once shut down, defueling commenced promptly and was completed by the late 1995. In parallel, the turbine and steam raising plant was removed to clear the turbine hall for the construction of the sodium disposal plant to neutralize both the primary and secondary coolant. This amounted to about 1,200 tons. This has been successfully completed, and the intention was to follow this with cleaning the remaining residues in the primary vessel by a controlled injection of water vapor in a nitrogen gas stream. In advance of this, a series of trials were carried out, initially at lab scale and then at kilogram scale, to demonstrate and justify the process. These trials identified that the process could not be as well controlled as hoped, and that where there were significant pools of sodium, it was possible for the process to pause due to a crusting of the caustic interface layer, allowing a buildup of moisture. This could then break through, leading to a runaway reaction. With this issue identified, the justification for pursuing the process had to identify the safe operating parameters within which to control it. Calculations were made which identified the maximum hold-up pool for which the resulting pressure pulse within the reactor vessel could be tolerated. This was assessed against the reactor vessel conditions following removal of the bulk sodium. The original inventory of 900 tons had been reduced to approximately 6, which was present in a number of hold-up areas. Most did not pose a concern, but the heel pool at the base of the reactor vessel was estimated to be approximately 1.8 tons, and this was too large a volume to proceed safely with the steaming process. As a result, a method of draining this sodium to a safe quantity had to be devised. There were two aspects to solving this problem. Firstly, to remove the sodium, it has to be in liquid form. With the bulk sodium removed, there was no means of keeping the remaining sodium molten. In the early days after shutdown, this had been done by running the primary sodium pumps until a sodium heater was designed, constructed, and installed through a vertical port in the top. With the bulk sodium removed, this heater was no longer operable, and the residual hold-ups within the reactor vessel had solidified. Secondly, a suitable pumping system had to be devised to extract a relatively small volume of sodium from 40 foot down at the base of the reactor. The original pump had not been able to extract the last remaining volume when it had removed the bulk coolant. Access to this area at the lowermost extremity of the vessel was extremely challenging, and during project planning it was apparent that there would be insufficient room to install both heating and pumping infrastructure from the reactor top. It was decided that the pumping infrastructure would make use of the reactor top penetration to keep the sodium removal process within the reactor hull, which meant that a means of heating the base of the reactor had to be done from below. The primary vessel is surrounded by a leak jacket designed to contain the sodium should there have been a failure of the primary vessel during operation. This combined structure was suspended within the reactor vault, which had cooling ducts for normal operation and was also designed with the ability to provide emergency core cooling should the reactor have suffered a catastrophic failure of both primary and leak jackets, flooding the vault with sodium. This area could be accessed via the forced air cooling ducts. An innovative concept of drilling through this leak jacket and the associated insulation, reflective stainless sheets and mesh was developed, along with deployment jacking mechanisms for the bespoke coring mag base drill. This is a good example of the type of task where extensive use is made of mock-up trialing to develop the best combination of core bits, drill feeds and speeds for each part of the complex drilling process. In tandem, an innovative petal heater design was developed and comprehensively trialled. These petal heaters were designed to fit through the smallest possible drilled hole via a sleeve system and then fold out into a 6-petal array once through the hole in order to create as great a contact area as possible on the underside of the primary vessel. Spatial constraints within the area between the primary vessel and leak jacket were extremely tight, and so a complex folding mechanism with damped arm elements was developed and tested until the team were satisfied that deployment was not only possible, but reliable and repeatable. In total, 11 heater arrays were installed effectively in this manner, and the comprehensive cable bundles were run into the vault to enable their activation from the reactor top. The heaters were set to work in April 2019, successfully melting the sodium, which was finally removed in March-April 2021. This task was impacted by the COVID pandemic, which restricted operations and resulted in a longer deployment period than originally intended. As a consequence, there was concern that the heaters would fail in service. However, their performance and reliability was exceptional. This has prepared the reactor for the next phase of the vessel cleaning, which is to passivate the residual sodium by steaming. This is going to be applied using equipment developed and installed into ISO container skids, which are currently being installed in the reactor hull. The strategies and techniques for the next phase of decommissioning of the reactors is currently being determined. Essentially, this is to carry out the remote size reduction and packaging of the internal structures. To optimize this process for PFR, the current strategy is to remove the long components from the reactor vessel and then size reduce them in a purpose-built cell within the reactor hull. Although cold cutting to free these components is being trialled in a mock-up test area in one of the old secondary heat exchanger vaults at the PFR, it is possible to use different cutting techniques for size reduction. The site has experience of carrying out active plasma cutting in PIE cells, as we can see in the picture on the right. This was reasonably successful, but the potential use of laser cutting technology is rapidly reaching a level of maturity for active deployment in reactors, and the airborne generation it causes is closer to 1/10 of that from plasma. In addition, the Dounreay site has had experience in the past of both laser cutting and laser welding, as both these operations were carried out on fuel subassembly wrappers in the reprocessing operation. But additional research is needed to validate the process for full-scale cutting of reactors. As a consequence, the final cutting techniques are still in development. Although not directly related to reactor decommissioning, I'm also actively pursuing the use of the potential of lasers to decontaminate heavily contaminated reprocessing plant vessels. The technique is starting to see early use in lightly contaminated metals at low-level waste category, but my interest is in the potential to deal with high active liquor storage tanks, where the only current option is chemical washout. This will require a suitable gaseous abatement system, as conventional HEPA filters will not be suitable for trapping the bulk particulate due to the volume and dose associated with the waste. So research is currently focused on determining the size and form of the waste arising. This will allow waste concentration as intermediate level waste and also address the problem of how to deal with the large active bulk storage tanks, which currently do not have a disposal route. The other interesting technology that is now becoming reality is the use of robotics. I come from the era when Star Wars hit the big screen for the first time, and androids and similar, particularly with artificial intelligence, were pure science fiction. However, it is no longer so, and these technologies have now reached reality and cost effectiveness. This is another exciting future opportunity for us to exploit and determine where we can best utilise these capabilities. It is difficult to predict where we will be in even 5 or 10 years' time, but it has the makings of an exciting future. I hope you have enjoyed my short presentation updating you on D&D decommissioning progress and some of our thoughts on the future.
Hi Gordon, thank you for joining us. It's a pleasure to have you here today. And it's really great as well to hear about Dounreay. I mean, it's internationally recognised now as one of the most complex sites, and its collection of different reactors, fuel plants, labs, etc. It's really unique. So thank you for sharing a snapshot of the work that's ongoing there. I'll encourage the audience to keep sending in their questions. But for now, I'll kick off. We've received some already. So I think I'll start off with one, that ties in quite nicely with your last slide and the themes of today's event. You mentioned in your presentation the value of modelling to overcome some of the challenges. And I wondered if you at Dounreay have used any digital twins for any of your projects. Well, somebody wondered, sorry, it's not my question.
Really just at the start. I mean, really, we're a bit elementary on that one. We have started doing sort of laser scanning and so on, but I'm kind of really thinking about where we could use this in the future, because when we can have, for example, power manips that can be controlled by computer, can we enhance this by using 3D point clouds, which have created effectively a digital map? Can we then use them to drive power manipulators? So, I mean, in direct answer, we haven't done very much, if I'm being honest, but we're aware of the technology and we're starting to explore it to see what the potentials are. Hopefully that kind of answers it a wee bit. We're a bit elementary, but we're trying to do it.
Brilliant, thank you very much. We've now got a couple of technical questions about kind of the progress with the decommissioning. And one relates to the DFR, and it says, in your presentation you mentioned about 75% of the fuels now being removed. When do you anticipate, you'll have removed all the fuel, and can you share a bit of insight into how significant the delays were with the crane rail fracture, please, Gordon?
Yeah, I mean, with regard to the fuel, first of all, we're obviously heading to the more problematic stuff, but nonetheless, it's going well. And at the moment, I think late summer next year should see the end of the fuel out of the reactor. With regard to the crane rail delay, this is what I'm racking my brain. I actually did the investigation into the crane failure, so I ought to know and I ought to remember, but I'm struggling. I think the delay overall was in the 4 to 6 months, approximately. But some of the issues that made it difficult was, one, first of all, identifying the cause of failure, but two, sourcing the rail, but also then getting the access to be able to change the rails, because it works. I mean, it looks quite nice in a photograph when you can see the floor plates round about, but in reality, there's not many areas where you can see the floor plates next to the rail. And we have to lift a lot of the rails. A lot of the area is actually C3 operating conditions, because the nature of the reactor means that's not exactly the cleanest place in the world. And so the work is actually a lot more difficult than it would be if you were just out in a nice clean building with a bit of space. So I think my recollection is it was in the 4 to 6 months bracket that got us back to being able to run on a limited operation. We still have some crane rails to change, so we're kind of doing work in between things so that we can keep the fuel moving as best as possible.
Thank you very much, Gordon. Now, we've also got a question about PFR. And in your presentation, you mentioned that now that you've completed removal of the sodium heel pool, that the next step was to get rid of the remaining sodium residues within the vessel. And I think you mentioned that you're going to be, I think we may have had some connection issues with Gordon there.
Yes, it just suddenly disappeared.
Okay, well, you're back now, so I'll continue with the question. It related to PFR. I think you mentioned in your presentation that now you've finished the sodium heel pool work, the next step is to use purpose-built skids to remove the remaining residues within the vessel. And I just wondered if you could share a bit more information on how that will be done and the timeline, if you can.
Okay, well, at the moment, the equipment's being installed, and then once installed, basically you feed in a limited amount of moisture in the nitrogen gas stream, because obviously we're still in inert atmosphere, and you're running it in at single figure percentages, and let the stuff slowly react to create sodium hydroxide, basically, which then you can pump away as a caustic liquor. So hopefully that shouldn't take very long, really, in the grand scheme. It's been a while to get to here, mind you.
That's often the case, isn't it, with nuclear? But you're getting there, and it's great to see the progress that you've highlighted across a range of facilities. I mean, that's what does it for me. It's they really are kind of unique, and you must be facing massive challenges. So it's great to hear about the innovations as well. We've just had another question in from someone in the audience, and they wondered if you can share more details about how you're going about your developing laser decontamination. I know you said again that was at early stage.
Yeah, I mean, the difficulty here, I suppose, is keeping it short enough for your presentation, because this is something I'm very interested in. But in very simple forms, lasers can ablate the surface of contaminated metals and elevate both metal and contaminants into the gas stream above it. What you have to then do is trap it out into a nice concise form. And in this sense, we don't want to use traditional HEPA filters, because we would end up with HEPA filters that would fill an aircraft hangar. But the other issue is, what are the particulate sizes and how small do they go down to, and can we make sure we trap them all? Because if we're doing really dirty ILW, then we've got a lot of stuff there, and we don't want even a tiny fraction of a percent escaping. So the moment the research is looking at what is the elevated particulate size rate, I always don't want to use the word particle, because we're analysing right down to atoms, to see what the size range is, and then how's the best to do it. So at the moment we have a number of studies running to assess what will be coming off, and then the next phase is to look at the abatement process that we would do to best capture all that material.
Fantastic. Thank you very much, Gordon. Unfortunately, we're running low on time. We've only got a minute or so left, so I just want to wrap it up. But again, thank you very much. If there's any further questions, we'd be happy to pass those on to Gordon. And I just want to encourage everyone here, if you've not done so, to visit the sponsor pages and to join the networking area at the end of our session. We've got one more presentation, and I'm looking forward to this one because it's from Canada and from Chalk River, and obviously that's again another unique site, and they're probably facing similar challenges. So I hope to see you there, and thanks once again, Gordon. It's really good to hear about the innovations at Doomray, so thank you for your time.